So this and the next slide, I will show some ideas or tricks or ways to reduce the number of cache misses. And in the Lab 0 program, we use the edges as well as everyone has seen. We have an edge with 2 nodes and the flow and the capacity. But it can be done in a more memory efficient and in also a cache friendly way. That each node has an array. I mean, this is a pointer, obviously, but it can allocate an array with all the edges. Okay, and then the edges can contain only the other node, but not a pointer to the other node, but just the index of the other node. So that cuts the memory requirement in half for that, and we avoid storing when we fetch an edge, it will not, I mean, this node does not need to know about itself, but somewhere it must be stored anyway. I mean, both for a certain edge, both nodes U and V will need this struct, obviously, with different contents, but I mean, the V node will be the other node for the other node. Okay, but to identify which edge it is, we can use an edge number and as an index and find the capacity and flow in some other way. Okay, and then we can have pre-computed in this organization or structure, we need to pre-compute the direction that we did during runtime in an if statement, checking if we are the U or the V. Okay, so this is cache friendlier in actually more than one way. First, it uses less memory since we don't need the pointer to the other node, and also a linked list. It is typically spread out in memory. It can be done in different ways. I mean, how we allocate the memory, but it's the edges can be located anywhere in memory, and then we don't benefit from the spatial locality. In this way, doing an array, and I mean arrays are usually very much better than linked lists, or since we get the benefit of spatial locality. And one more point that I will come to later in this lecture. Well, I can mention it soon. So when we have an array, we will fetch all of these edges that fill 128 bytes. So we get only one cache miss for all these edges. Okay, so we can do that. It's natural to do that in a graph where the data doesn't change. I mean, the graph doesn't change. The data structure is somewhat more complicated, but I want in Lab 0 and the Scala program and the distributed versions of different programs, I wanted to have as simple structure as possible. Okay, to optimize the time to understand the program. Okay, so this is one option, namely to use smaller data structures instead of pointers. Okay, so then the question becomes, which type should be used here? Well, we need to know how many nodes there are. If there are several, I mean, a sufficiently large number, which is larger than that we know an int can index, then we need to use some other type, and maybe that type will be 64 bytes, so it's the same size as a pointer, and then there's no point in using an index. But maybe we know that there are only, I mean, if that the short int is sufficient, that's 16 bits. That's short int. That may be sufficient, and then we can use that, for instance, but not in the input that we have seen. Okay, I mean in the course. Okay, another thing that we can do is to insert wasted memory between structs. So say if we have a cache block like this, and we have okay, like that, and the struct that we fetch is here in this. So then we get first the cache miss here, and then when we want a field of the struct here, we get another cache miss. Okay, so what can we do then? If we can first of all allocate the first element in an array of such structs so that it is located at the beginning of a cache block. Let's see what can happen. Say the first element is there, and then the next, and then we can say that the next will end there, the third. Okay, so I mean these three don't fill a cache block, but if, well, it will not be so easy with 3, but okay, we say 4 instead, that they have this size. Okay, and now the fifth struct will start here. Okay, and we get this unfortunate that we need to access it from 2 different cache blocks. Okay, so padding a struct, what does it mean? It means adding some, say there are 8 bytes here. This is just an example, but if we could increase the size of each of these 4 structs by 2 bytes, then they will fit perfectly in a cache block. And how can we do that? Well, we can end the struct with an array of the required size. Okay, so we can end it like that, or we can insert a short int variable, or I mean we just increase the size with 2 bytes, and then they will fit perfectly into a cache block. Okay, padding in this way is used to improve the performance. Padding actually happens in other situations as well. Say we have a struct here, and we use a double, and then we use a car, and then we use another double, so that we might expect that so far we have used 17 bytes. Wrong. What this needs instead is this is 8 bytes, and that one is 8 bytes. Okay, and the double must be located on an address which is a multiple of 8. And it's the same for other data types. Okay, so that means the compiler will allocate 1 byte for the car and 7 bytes padding. Okay, so these 3 will take 24 bytes instead. And these 7 bytes are clearly unused and should be avoided if we want to reduce the amount of memory that our structs need. Okay, so one way to avoid it is to store, to put the attributes of a struct or the fields of a struct, the largest ones first. Then we reduce the amount of padding. Okay, another idea is to put the attributes that are needed at approximately the same time, or at least so that they are fetched at the same time when we get the cache miss. That depends on how big the struct and the cache block size are, of course. I mean, we have to think about that.